Hi everyone, we are Group 10 and we're going to be doing a walkthrough of Chapter 9, Optimizing Cost and Quality. As the name suggests, this chapter focuses on how to make large language models more efficient and cost effective, as tools like GPT-4 are powerful but extremely expensive at large scales. Our team consists of Peng Qi from the Department of Computer Science and Engineering, as well as Angela, Yu Hui, and John from the Department of Data Analytics. Here's a quick roadmap of what we'll cover. First, we'll start by introducing the cost problem, which is really the motivation behind everything in this chapter. Then we'll walk through four main optimization strategies: model tuning, model selection, prompt engineering, and fine-tuning. Each comes with their own individual trade-offs, which will be explained and demonstrated with concrete numbers and code examples throughout. And finally, we'll wrap it up with key takeaways, what actually works best and when. This chapter starts with a really important observation, which is that using large language models at scale can get expensive very quickly. To make this more concrete, let's ground this in a real scenario. Imagine a company called Banana Corporation that collects customer reviews on its products. Now, these are just free-form text reviews, and the goal is to classify each one as either positive or negative. Let's say that Banana Corp receives 10,000 product reviews daily, and each review is roughly 100 tokens. That's 1 million tokens per day, or 365 million tokens per year. If we use a large model like GPT-4, which costs 6 cents per 1,000 tokens, that comes out to nearly $22,000 per year just for classification. However, if we switch to a smaller model like GPT 3.5 Turbo, which would cost about 1/20th of a cent per 1,000 tokens, that total comes out to just $182 per year for the same task. Our question now becomes, can we maintain acceptable quality with the cheaper model? And that's what this chapter is all about. Our toolkit has four main strategies to help us tackle this cost problem. First is model tuning. This involves adjusting parameters like temperature or token probabilities to control how the model generates responses. For example, lowering the temperature makes outputs more consistent and deterministic, which is especially useful for tasks like classification. So instead of changing the model itself, we're just changing how it behaves. Second is model selection. This is often the simplest and most impactful strategy. We choose a smaller, cheaper model that still performs well enough for the task. As we saw earlier, switching from a large model to a smaller one can reduce costs by over 100 times. The trade-off, of course, is that smaller models may be less accurate, so we need to evaluate whether the performance is still acceptable. Third is prompt engineering. This means carefully designing the input we give into the model. Even small changes in wording can lead to very different results. One common technique is few-shot learning, where we include a few labeled examples directly into the prompt to guide the model towards the correct format and behavior. And finally, fine-tuning. This is the most involved approach. Instead of just prompting the model, we actually train it further on a small task-specific dataset. This allows the model to specialize and often achieve higher accuracy, but this comes with an additional upfront cost and complexity. So overall, each of these methods gives us a different way to balance cost and performance. Now, let's start with the simplest possible implementation, our baseline model. In this setup, we take each review and send it directly to a model like GPT 3.5 Turbo, using a very basic prompt that just asks the model to classify the review as positive or negative. We also set the temperature to 0 to make the outputs consistent and reproducible. At first glance, this seems like it should work fine, but when we actually tested it, the results are not too great. We only get about 60% accuracy, meaning the model is only correct 6 out of 10 times. When we look closer, we see two main issues. First, the model sometimes predicts the wrong label. But second, and just as important, it doesn't always follow the expected format. It might return something like negative instead of the required label, neg, for negative. So now we have two problems to solve, improving accuracy and ensuring consistent output format. This baseline gives us a starting point to apply the four optimization strategies and see how much we can improve from there.
So for our first key optimization strategy, it is model tuning. And in model tuning, one of the ways you can fix format errors is the logit bias. The logit bias parameter lets us increase or decrease the probability of specific tokens. When we looked at our label tokens using OpenAI's tokenizer, the positive POS had a token ID of 981, and the negative, or just shortened to NEG, had a token ID of 29875. So once we found those specific token IDs, we were able to set them to both have a maximum bias of plus 100. However, there was a negative repercussion to that, and now, without limiting the output length, the model can only produce positive and negative tokens. Therefore, as you can see here, it can't produce a stop token. So the model gets stuck when trying to classify the very first example by endlessly generating the negative token over and over again and never getting to the second example. This leads to obviously unwanted result with 0% accuracy and a massive cost. This kind of showcases, though, the importance of understanding the interaction between different parameters, as we need to limit the output, but also still be able to produce stop tokens. A simple fix to the problem on the previous slide is to add max tokens that are equal to 1. Since our class label is positive and negative are each a single token, we only need one output token. So when we combine max tokens equaling 1 with the logit bias forcing those to only be positive and negative tokens that are output, we get our guaranteed valid output that is only one token long. With these settings, the accuracy result jumps from 60 to 70%, which is a 10% improvement at the same token cost. On our example with only 10 inputs, going from 6 correct answers to 7 might seem insignificant, but when applying this technique to a full data set, it would result in thousands more correctly classified reviews. Our second optimization strategy is model selection. Switching to GPT-4 with the same tuning parameters on the last example gives us 80% accuracy, which is another 10% improvement. So the token count stays the same at 2,228 since both models use the same tokenizer, but GPT-4 costs 6 cents per 1,000 or for 1,000 tokens versus GPT 3.5 has a 0.0005 cents per 1,000 tokens. That makes GPT-4 120 times more expensive for only a 10% performance increase. And so for our yearly scenario, that cost difference would look like $21,900 for GPT-4 versus $182 for GPT 3.5. And so obviously with that massive price difference, you get some key questions like, can we achieve GPT-4 level quality while staying on the significantly cheaper GPT 3.5. And that's where our third technique comes in with prompt engineering. However, before we look at our next technique, we also wanted to look at an actual error case. At the start of this review, we see a negative phrase, this is not the film for you. This phrase would normally be a strong enough indicator of a negative review, but then as the review continues, we see multiple positive phrases such as, this is the movie for you, and all stops are being pulled out. The truth is that this is meant to be a mostly positive review, but only recommended to certain viewers. And we see that GPT-4 seemingly understands this and correctly predicts this review as positive, whereas GPT 3.5 kind of overvalues the first negative phrase and marks the entire review as negative. But this is an ambiguous case that isn't clear kind of without deep insight. So it's, one has to ask, is it worth spending 120 times more money to correctly classify this borderline case and others like it? At the cost, it may not be worth it to you and your business. However, in a more serious setting with maybe more impactful predictions, you might be in a situation where every single percent increase may be priceless and therefore justify any cost increase. So a key takeaway is that examining your invalid predictions is very important. Therefore, it is up to the user to kind of understand if the borderline cases justify a massive cost or time increase.
Prompt engineering is about designing better prompts to improve model performance. More specifically, it means modifying more prompt templates to significantly influence the quality of the model's output. Instead of changing the model itself, we change how we ask the question. That is important because as the chapter emphasizes, prompt design can have a significant effect on performance, sometimes even comparable to changing the model. The core goal is to help the model better understand the task and produce more accurate and consistent outputs. The main technique we focus on is few-shot learning, which is one of the most effective and widely used prompt engineering methods. So now let's look at how few-shot learning actually changes the prompt. Prompt engineering is about design better prompts. The key technique here is few-shot learning, providing examples of correctly solved tasks. On the left, our zero-shot prompt just asks for classification. It only includes the reveal and instruction. On the right, the one-shot prompt first shows a sample reveal together with its correct label and then asks the model to classify our target review. The sample is color-coded. Amber for the sample review, green for the provided solution, and blue for the review we want to classify. So virtually, we are clearly separating example, answer, and new task. But the key idea is not just adding an example. What we are really doing is showing the model a pattern. What does the input look like? And what the correct output looks like. Another important detail from the chapter is that we use the same structure twice, once for the sample and once for the review to classify. This repetition helps the model following the same format and generate consistent outputs. The intuition is the same as human learning. It is easier to understand the text when you see an example first, rather than just reading a description. So now that we understand how the prompt changes, let's break down its structure more clearly. The slides break down the structure of one-shot prompt. There are 5 parts. First, the sample reveal. This is the example input. Second, the text instruction and answer format, which tells the member what to do. Third, the sample solution, which shows the correct label for the example. Fourth, the review to classify, which is the actual input we care about. And finally, we repeat the text instruction and answer format again for the new review. The key idea here is consistency. We use the same structure for both the example and the target task. As the chapter points out, this repetition makes the prompt slightly redundant, but it helps the model clearly follow the pattern. In other words, instead of just describing the task, we are demonstrating exactly how it should be done. Now the question is, does this actually improve performance? And there's the payoff. Adding just one sample review to each GPT 3.5 prompt achieves 80% accuracy, matching GPT-4. So with a better prompt, a smaller and cheaper model reaches the same performance as a much larger model. Now let's look at the cost side. Token usage roughly doubled from 2,228 to 4,078 because we are adding a full sample review to each prompt. So every single request becomes longer. But even with double tokens, GPT 3.5 with one-shot learning is still about 60 times cheaper than GPT-4. At scale, that's about $365 per year versus $21,900 per year. This is a massive saving for the same accuracy. So this result highlights a key insight from the chapter. Improving the prompt can be more cost-effective than switch to a large model. That's why prompt engineering is often the first thing you should try before increasing model size. So once we know the prompt matter, the next question is how do we systematically test different prompt and parameter combination? To make experimentation easy, the book provided a tunnable classifier that accepts all parameters via the command line. You can specify the model, max tokens, tokens bias, number of few-shot samples, and the sample fill pace. This means we don't need to rewrite the code every time we want to try a new setup. Instead, we can quickly test the different combinations, for example, GPT 3.5 with bias and one sample, or GPT-4 without bias but with multiple samples. So this tool acts as a unified experiment framework. It brings together everything we have discussed: model choice, prompt design, and parameter tuning. The key takeaway here is systematic experimentation is crucial. We should test different configurations on a small sample data size first, because it is cheap and fast. Then, once we find the best setup, we scale it to the full data size. This approach helps us balance both cost and performance, which is the main theme of this chapter.
Fine-tuning is our last resort when other methods aren't enough. The idea is take a pre-trained model like GPT 3.5 and specialize it with our own label data. The process has 4 steps. Prepare the training data, upload and run the fine-tuning job like it will take about 50 minutes, and get a customized model, and then deploy it. The key advantage is dramatically simpler prompts, which is the fine-tuned model already knows its task. So you just send the review test with no instructions, no examples, no label descriptions. Training data for the fine-tuning must be in JSON-L format, which is like this. So you can see that each line is a JSON object representing a successful model interaction. We convert our CSV reviews into user assistant message pairs, which is like this. The user sends the review text and the assistant responds with the correct label. The code to start fine-tuning is straightforward. Upload the file, create a job, and wait for about several minutes, maybe like 15 minutes, you will need at least 50 samples for the fine tuning to be effective. And our sample here, you can see we use this 100. So here is the full comparison table. So basically, fine-tuning achieves 17% accuracy with simpler prompts and fewer tokens, which is like you can see here. It's like three. It's 2085 versus 2228, but the per token cost is 6 times higher at 0.003 per 1,000 tokens. The moderate token saving don't offset the higher price. In this scenario, GPT 4.5 with one-shot learning wins. You can see the 18% accuracy at about $365 per year. Fine tuning is most valuable when you need very high accuracy on a well-defined task and have enough training data. So always run the cost calculations for your specific situation. That's the best advice I can give you. Okay, so the slide brings it all together. On the left, accuracy for each configuration, and on the right, estimated annual cost at scale. GPT-4 achieved 80% accuracy, but at a staggering 21 and 900 per year, and GPT 3.5 with few shot learning matches the accuracy for just 365. Fine tuning sits in between at 1095 with only 17% accuracy. The clear winner for the task is GPT 3.5 with few shot learning, so which is the best cost quality trade-off. But remember, this depends on the specific task, and always evaluate on your own data. So a few practical tips from this chapter. So first, always evaluate on samples before scaling. The upfront cost is tiny compared to running the wrong configuration on millions of reviews. And also check the Stanford's Helm benchmarks for the model comparisons, and systematically try all available parameters. If you are stuck on prompts, performs like prompt-based, they actually have community solutions. Fine-tune only at a last resort after exhausting simpler method, and most importantly, always do the math. The cheapest per token price isn't always the cheapest overall solution. So this is our key takeaways. And to summarize, first, parameter tuning like logit bias and max tokens provides free quality improvements. And second, don't default to the biggest model. Just smaller models are dramatically cheaper and often sufficient. Third, prompt engineering, especially few-shot learning, is often the most the cost quality trade-off. And fourth, fine-tuning is powerful but comes with overhead, so you might want to do the math first. And fifth, always evaluate the systematically on samples before committing to a full-scale run. The optimal strategy depends entirely on your specific task, data, and budget. So here is a practical decision guide. So start with the parameter tuning, it's free, and then try prompt engineering with few short examples. And next, evaluate alternative models. Only fine-tune as the last step, and always run cost-benefit analysis first. The decision matrix, here you can see the matrix labeled with different color. It really helps. If labels are malformed and just like this, you can add the logit bias. And if the accuracy is too low, you can add examples. If still not enough, you can try a bigger model. If the cost is too high, you may want to fine-tune a smaller model. So work through these steps systematically on a sample before committing. So yeah, so that's all for our presentation. Thank you so much for your attention. We are very happy to share all this information, and we are ready to take any questions about the optimization strategies we discussed, or about how to apply these techniques to your own projects. So the last word and also the key message we want to deliver here: you don't always need the biggest, more expensive model. With the smart tuning, prompt design, and the right model choice, you can achieve greater results at a fraction of the cost. Thank you so much for listening.